Okay, this video is about the other major operation between matrices called matrix multiplication. This is far less intuitive than the previous operations between matrices, but it isn't too bad once you get used to it. Okay, so let's go ahead and start first with a comment. Not every two matrices can be multiplied. There are some dimensional requirements. Okay, so just like addition and subtraction, remember there were dimensional requirements on those operations. Basically, the conditions were that the matrices had to have the same dimensions. Now we have a different restriction here when we're talking about taking products of matrices. Okay. Now another thing that we're going to have to be aware of is that matrix multiplication is not commutative. Okay. That means even if both the matrix products AB and BA exist, and we'll see conditions under which that is true, they still may not be equal. Now you remember the commutative property from regular real numbers here. A times B is equal to B times A. Now sometimes that's going to be true when you multiply matrices, but sometimes it's not going to be true. And in many cases, as we're going to see, even if one product is defined, the other may not be. But even if they're both defined, they may still give different results. Okay? Now, here's the condition, the dimensional conditions for the matrix product to exist. Okay? Okay, now, order is important then. That's what I'm saying above here when you're talking about multiplying matrices. Order is important. So here I've got A on the left and B on the right. In order for the matrix product AB to exist, the number of columns of A must equal the number of rows of B. Okay? This is necessary and sufficient condition for the product A times B to exist. Okay? Now let's go back and just to make it easier here, write down just a little bit of our notation for dimensions here that might help us out. Remember, if you've got a matrix A here on the left here, and its dimensions are m by n, m indicates what? The number of rows, and n indicates the number of columns. Okay? And B over here on the right, let's say its dimensions are what? N rows and p columns. My point is these must match here. See what I've written here? These two, the circled next to each other, these two must match, otherwise your product doesn't even exist, okay? So this is just what I said above. The number of columns of A, which is indicated in this case by n, has to be equal to the number of rows of the matrix on the right, which we are calling in this case B, and the number of rows there must be n also, okay? So these have to match. Okay, another little thing I'm going to throw in here, okay? Necessary and sufficient conditions there are satisfied for the product, in this case of A times B to exist. The dimensions of your product, of the answer, in other words, is going to be M by P. Okay? So it's going to be the outer dimensions here. The number of rows in A by the number of columns in B. Okay? All right, so those are going to be the outer numbers here. All right, now this may look confusing, but we'll have to get used to it here. Okay, we'll be looking at some concrete examples. We're going to start by multiplying a matrix by a column vector on the right. Okay, so this is how I'll teach you to multiply matrices. Okay, now, so I'm going to take this matrix. Notice this matrix on the left is a 2 by 2 matrix. As you can see, there's 2 rows and 2 columns. The matrix on the right is what we were calling a column vector. That is what? It only has a single column, but it has what? 2 rows. So it is a 2 by 1. Now notice that what? These two numbers here match on the inside, right? I've got those circled. Those match, so you can actually what? Take the product in this order of those two matrices, okay? What's the answer going to be? Or the dimensions of the answer? Well, we'll get what the answer is in a second. But the dimensions of the answer is going to be what? a 2 by 1, which makes 2 rows and 1 column. So it's going to look rather like this vector matrix, right? It's going to be a vector with 2 rows, a column vector with 2 rows. Now, for actually how we multiply here, and I'll show you, and you can see immediately why we have the conditions on the dimensionality. Okay, now here's what I want you to see in your mind here. I'm going to start with this column that's over on the right, the 5, 1, and I'm going to lay it down. I'm going to take in my mind its transpose. Remember transpose from the previous video? Okay, that's where you interchange rows and columns, right? You turn columns into rows and rows into columns. In this case, there's 1 column, and that's going to be changed into 1 row. Now, this is a little thought cloud, okay? So this is just what I see in my mind. You can actually write this on your paper, but use pencil because when you get larger matrices, you're going to have to erase the 5 and the 1. Okay, but anyway, so I've taken in my mind the transpose of 5, 1, and as a column matrix, and it became a row matrix, or a row vector. Now here's what you do. Do you see how I have a match between these? I have what? These are matching up, these numbers here, right? There's as many here as there are here. Now what you want to do is take the product of corresponding entries and add them up, okay? Starting with the first row, and that's going to give us the first entry of our answer. So I've written that here. So this is going to be 1 times 5 plus, that's the add up part, 3 times 1, okay? And that's going to be what? 8, okay? You can see a little mental arithmetic there. Okay, and then do the same thing with the second row. So that's going to be what? 2 times 5, I've got there, plus negative 4 times 1. Okay, and then just do the arithmetic. That'd be 10 plus negative 4, which is 6. So the answer is 8, 6 as a column vector. Okay? Alrighty, so there it is. That's how you multiply matrices. Okay, well, at least by a vector on the right. Okay? All right, let's keep practicing some more. Okay, let's do another example. Okay, I know it looks kind of weird here. Okay, by the way, the dimensions on this one I did not write, but this is what? This is 3 by 3, as you can see. And the one on the right is what? 3 by 1. Okay. Now these two match. Okay, so that's cool. So we can actually take the product. Okay. And the answer is going to be what? A 3 by 1. So it'll have 3 rows in a single column. So it'll look rather like that vector. Okay. Now what do? You take the transpose of the 2, 6, negative 7. You could just do this mentally if you want, or I've physically written it okay, for your convenience here. Okay, so I've got 2, 6, and negative 7. Now I'm going to start with the first row here of the matrix on the left. We're going to take products of corresponding elements and add them up. Okay, so I'm going to go 1 times 2 plus 0 times 6 plus negative 1 times negative 7. And I've written those numbers right here for you conveniently. Okay, we'll do the actual arithmetic in a minute. Okay, let's go to the second row. So don't leave until you're done with what? All the rows here. So it's going to be what? 2 times 2 plus 3 times 6 plus 0 times negative 7. Again, I've written that there. Okay, there it is. And then finally with the third row, take the product of corresponding entries here with what? When I say corresponding entries, with these numbers floating on top here, right? 5 times 2 plus 4 times 6 plus 1 times negative 7. Again, all written there. Okay, when in the beginning you might like to write these out for yourself. Okay. You do the mental arithmetic if you want, but you need to be careful. So that's 2 plus 0 plus 7 is 9. There we go. Okay, that's 4 plus 18 is 22, because we're adding 0 at the end, right? Okay, 10 plus 24 is 34, plus negative 7 is, what, 27? Is that right? Oh, wait, I got it wrong. Let's correct that. That should be 27. Okay. You're not wrong if you don't have to erase. Just remember that. There we go. Okay. Alrighty. Okay, so not so bad. Again, this is a 3x1 matrix. Okay. But, oops, that actually changes it to red here. It's kind of goofy. You can see that this is a little bit weird. I could put this in a greater context here, but that might be kind of abstract for you right now. If you just follow the rules, you should be okay. But you have to be able to do these by hand, okay? All right? They do have calculators and computers that do this for us, but you need to know this by hand for the exam, okay? All right. Well, we practiced a couple where we were multiplying on the right by column vectors, right? Now let's practice just multiplication on the right by matrices that have more than one column. Okay? So I'm going to go like this. This is amalgamation of the first one and a different one here. Okay, so I've got 1, 3, 2, negative 4 times what? 5, 0, 1, 6. Now let's look at the dimensions on each first. The matrix on the left is a 2 by 2, as you can see, and the matrix on the right is a 2 by 2. Okay? These two numbers match, right, on the inside, so the number of columns on the first matrix, reading from left to right, is 2, and the number of rows in the second matrix, reading from left to right, is 2. These match. So what's going to be the dimensions of the answer? It's going to be, a 2 by 2 also. Okay? So you can see what's going to happen in general here. A 2 by 2 matrix by a 2 by 2 matrix is a 2 by 2 matrix. Okay? Alrighty. Now, let's go ahead and do this. Now, how do you do this when you're multiplying by more than one column? All you do is what we were doing before, but you do it column by column. Okay? You do it column by column. Okay? So what I'm going to do here is imagine going 1, 3, 2, negative 4 times 5, 1. Okay? And that will form the first column of my answer. Okay? So we just imagine that that you're just multiplying by a vector now, and you're working it out just like you did before, okay? And then write down the answer, but you got to write some more room here because there's going to be a second vector you're multiplying by, a second column vector, right? A second column, really, and that's going to fit in right here. But the idea is going to be the same in both cases. So see what happens when I go like this. When I go 5, 1, and it multiplies on this matrix. So it's going to go what? 1 times 5 plus 3 times 1. Okay? And then the bottom row, okay, first element in the bottom row, the second row, is going to be 2 times 5 plus negative 4 times 1. Okay, so this is just exactly what we did before. Okay? And that now I'm done actually multiplying with the 5, 1. I'll do the actual arithmetic in a minute here. I need the form of the answer first. So now it's going to be like starting over one of our previous problems, only we're going to be multiplying on the right with what? The column vector 0, 6. So it's going to be 1 times 0 plus 3 times 6, which I've got written here. Okay? 2 times 0. This should be what? 2 times 0. Did I make another mistake? Gosh, I can't believe this. Shouldn't write it out for so fast. Okay? 2 times 0 plus negative 4 times 6. So this should be, what? Negative 24. Because this is multiplying on 0. So this should be 4 times 6 is negative 24. Okay? Okay. Let's see if we did the rest of my arithmetic correctly. I'm starting to wonder here. Okay, 5 plus 3 is 8. Cool. 0 plus 18 is 18. Very good. 10 plus negative 4 is 6. 0 plus negative 24 is negative 24. Okay, so we're good now here. All right. All right, let's try another one then. Okay, let's try this one. Let me go over to red again. Ready? So I've got 5016 times 1, 3, 2, negative 4. Again, this product should exist, right? Okay. All right. So you see what I'm going to do? All right. You're good at it, getting better. This is why I gave a lot of practice problems on this, so you can get used to it, because I know it's kind of strange. Okay. So imagine multiplying by what? This column as a vector and this column. Okay. Getting the columns of my answer. Okay. So when I do this, it's going to be what? 5 times 1 plus 0 times 2, I've got there. Okay. 1 times 1 plus 6 times 2, I've got there. Okay. I guess I'll do the arithmetic real fast here. That's 5 plus 0, so that's 5. Okay. 1 and 12 is 13. Okay. Now I'm going to multiply with the 3, negative 4. So that's going to be 5 times the 3 plus 0 times the negative 4. Check. Okay. And then it's going to be what? 1 times the 3 plus 6 times the negative 4. Okay, let's see if I did my arithmetic correctly here. That'd be 15 plus 0, so that's 15. That'd be what? 3 plus negative 24 is negative 21. So we're good. Okay, now there's a lesson here. The reason why I did this, notice that I just, these two problems, all I did was what? I just interchanged these two. So if I called this one A and this one B, in the second problem I have what? B times A. I just changed the order in the product here, right? In forming the product. So I have A times B versus B times A, so to speak, okay? Notice that these answers are rather completely different, right? These aren't the same matrices. They're both 2 by 2, yeah, but they're completely different, you see? So do you remember what I said, that matrix multiplication is not commutative in general? That does not mean that they're never equal. It's just sometimes they may not be, okay? So A times B equals B times A is false generally, but is sometimes true, okay? Alrighty. Okay, maybe this is a quick time to just point out here. Do you understand now why the number of columns here and the number of rows here have to be equal? I hope so, because you notice when we take what? It's transpose of each column, we have to have what? You have to have corresponding entries to multiply and add up, right? If there's a different number of elements in these different rows or columns, then you're not going to be able to do that, okay? Under what conditions do the products A times B and B times A both exist? Not equal, just both exist. Notice that these are not equal up here, but they both exist. The answer is A and B have to be square matrices of the same size, the same dimensions. Okay? Alrighty? All right. Now let me show you something else here, a certain special product, really. Okay, let's do this. This is what I'll call example 5. Notice I have a general 2 by 2 matrix here, and I've got a very specific 2 by 2 matrix here, and I'm going to take the product. So I just went like this, A, B, C, D. Okay, A, B, C, D can be any numbers. They could even be complex numbers, by the way. Okay, now let's take the product here. We know the answer is going to be a 2 by 2, just like the previous examples, right? Okay. Now, when I take the product here, again, practice this column by column. Okay. So starting with that first column of the matrix on the right, go ahead and multiply here. I'm going to have A times 1 plus B times 0. Okay. And that ends up being just plain old A. Then I'm going to have C times 1 plus D times 0. That's C. Okay. Now multiply with this second column. That's going to be A times 0 plus B times 1. Think about that. That is just B. And then what? C times 0 plus D times 1. That's going to be D. What do you notice here? When I have the matrix A, B, C, D, and I multiplied it by 1, 0, 0, 1 on the right, I got that same matrix A, B, C, D back. Okay? It didn't change it, did it? It didn't change that matrix on the left at all. How about if I turn this around? Let's try this. This exists, right? They're both 2 by 2 matrices. Let's turn it around and go 1, 0, 0, 1 times the A, B, C, D. Okay? Again, we're going to multiply column by column. Okay. All right. Here's what we would have then. We'd have what? 1 times A plus 0 times C. Okay. What does that boil down to? That boils down to A. Looking good. Okay, so for the second row in the first column of our answer, we'd have 0 times A plus 1 times C. That's just what? C, isn't it? Okay, multiplying with the second column, we'd have 1 times B plus 0 times D. That would just boil down to B. And then what? 0 times B plus 1 times D. That would end up being just D. What do we have again? We have the same matrix again, A, B, C, D. Okay? Notice that these two products are indeed equal this time, okay? Which usually doesn't happen, right? But in this case, when I was multiplying with the 1, 0, 0, 1, these two products are equal, and the quote-unquote variable matrix, that's the one with A, B, C, D, is unchanged after multiplication in either order. Okay? Well, I didn't write order there, but I said it verbally there, in either order. Okay. Very cool. And we have a special name for this matrix, 1, 0, 0, 1, because of this property. Okay. Because of that property, we have a special name for this. This 2 by 2 matrix, 1, 0, 0, 1, is sometimes designated by I subscript 2. Sometimes in certain contexts, you might just write cap I, by the way. And it's called the 2 by 2 multiplicative identity because of that, right? Okay? Because what? If you start out with a matrix 2 by 2 matrix A times I2 is the same as I sub 2 times A is A. And we just, for a proof of that statement right there, we proved it just above in the previous example, didn't we? Okay? Because remember, the matrix that I took was completely general, A, B, C, D, for a 2 by 2. Okay? What is the 3 by 3 multiplicative identity, do you think? What does it look like? Okay, I'm about to show you. Give it a second. Okay. Yeah, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? This is the 3 by 3 multiplicative identity. Okay? Oh, by the way, I throw this in for the sake of completeness. 1 by 1 matrices we don't really use too often because they just represent numbers in square brackets. Right? Okay. But just for the sake of completeness, the 1 by 1 multiplicative identity would be just the matrix with 1 in there. Okay. Remember, the real numbers have a multiplicative identity just being what? 1. 1 times A is A times 1 is A. Okay. What's the n by n multiplicative identity? Okay, so I'm being general here. Is the n by n matrix with 1s down the main diagonal and 0s for all other entries. Now, the main diagonal is this. Starting up the upper left-hand corner, like reading a book, right? Go down diagonally to what? The lower left-hand corner, and those elements are the main diagonal elements on a square matrix, okay? Those are the main diagonal elements. To form the n by n identity, you make what? The main diagonal elements all 1s, and then 0s everywhere else. Okay, so all other entries are 0. Okay? Alrighty, let's keep going. Let's talk about products of identity matrices with non-zero matrices, non-square matrices. Okay? Okay, I'm going to give you this example, and I'm going to introduce some other slight thing here, just for your sneaking stuff in here. I've got this matrix A here. So I said A equals, this is, you can see, is a 2 by 3, 2 rows and 3 columns, right? I'm going to introduce now what's called a double subscript notation. That's really not that important for what I'm about to do, but this is a good time as any to introduce it. Okay, this is double subscript notation. These are subscripts here. Now I'm using little a because our matrix is cap A. Okay, if this was cap B, I would probably use little b for the entries or the elements inside the matrix. Okay, now the double subscript notation, look at this. What is it telling you? It's little a sub, okay, or subscript sub 1, 1. What is the first number telling you? By the way, if these numbers get really large, you'd probably use a comma between them, but most people don't for small numbers. So it's not a subscript 11, it's a subscript 1, 1. But anyways, what's the first number that you run into? What is that indicating? It's indicating which row you're in, okay? What is the second number you run into? That's indicating which column you're in. So little a subscript 1, 1, or a sub 1, 1, that is what? The element of the matrix A that's in the first row and the first column. Therefore, this element right here, what? A sub 1, 2, that's in the first row and second column. Okay? A sub 2, 3, that's in the second row and third column, and so forth. You see? Do you understand double subscript notation? It's pretty easy here. Okay? It's pretty easy. Not too bad. Okay? Now, so I just threw that in here as a convenient time to do it. What I really want to do, though, is do the following. Suppose I have I sub 2, right? The 2 by 2 identity, and I'm going to multiply it on A. Now, just a quick little thing here. Notice that I sub 2 is a 2 by 2 matrix, and A is 2 by 3. I can clearly multiply these two, right? Because what? These two numbers match here, right? My answer is going to be a 2 by 3, just like what? The dimensions of A itself. Okay? So I've got 1, 0, 0, 1 times the matrix A. Now I want you to do this, okay? Actually multiply this out yourself here just for practice, but you're going to see here that you actually just get what back? You get A right back. So an exercise for you. This is so easy, you can really do it in your head if you understand matrix multiplication. But I know it's new to you, so you might need to write out a little bit more to get comfortable with it. But what is I sub 2 acting like on this 2 by 3 matrix? It's acting like a multiplicative identity on the left. Okay? All right? Now, I can't turn these around and go A times I sub 2, right? A times I sub 2, well, that wouldn't have the right dimensions, right, to multiply them. Okay? Because A is what? Like I've written here. That's a 2 by 3. It has 3 columns, so the matrix on the right better have 3 rows. Okay? Now, so I'm multiplying it by not what? I sub 2, but what? I sub 3. The 3 by 3 multiplicative identity. Okay? Our answer should be what? A 2 by 3 matrix again, just like A. And not only is it just like A, it's exactly A. If I actually take the matrix A here, there's its elements, okay, there's its entries, and multiply by the 3 by 3 identity. Again, you practice this exercise for you. Okay, it's real easy here. You get A back. Okay, so that what? I sub 3 on this matrix is acting like a right identity. Okay, in other words, if it's multiplied on the right by that thing, you get A back. Okay, so the various identities that we have or even work as identities for non-square matrices, but you have to take dimensionality into account. Be a little bit careful here. Okay? Okay, this is multiplicative identities. By the way, just to remind you from, so this was the 2 by 2 multiplicative identity. So if I multiply this matrix by any 2 by 2 matrix, for example, I get that same 2 by 2 matrix back. Okay? What's the additive identity for 2 by 2 matrices? That would be the matrix which, if I add to any 2 by 2 matrix, I get that same matrix back. This is quite boring. This is what? The matrix, 2 by 2 matrix consisting of zeros. Okay, well go ahead and you should be able to work those problems now. Okay, Alrighty, hopefully you understood this. Get that practice in there, okay? Because it's maybe a little strange. Okay, bye.